Hello, my name is Felix Fiedler, and this is the control LightPod from the Laboratory of Process Automation Systems. And as always, I am here with Professor Sergio Lucia. Hello, Sergio.
Hello, Felix.
And today, Sergio, we are going to talk about the topic Kalman filter.
Exactly.
So to get us into this topic, I'm going to show some content, and then I have a question attached to that content. And that question is, well, what is a Kalman filter? When do we need it, and how do we use it?
Exactly. So first, have a look at the context we are working with. Yeah, we are in the context of linear dynamic systems. We have here a typical description AX plus BU and some output equation Y equal to CX. Yeah, we want an estimator like a Kalman filter because we typically have access to some outputs Y, but we want to have actually the states because we base our analysis or maybe our control algorithms based on the knowledge of the states. So we want to have the Kalman filter to reconstruct those states based on the measurements.
Right. And then there's also something else in these equations, and that is this W and this V. Can you explain what these are?
Yes, those are the assumptions that we have in the Kalman filter setting, that we have some process noise affecting our dynamics. So this means that our system is actually not perfectly linear, but it has some variations around it. And we have some noise on our measurement, so we cannot measure perfectly.
Right. And these noises also need to satisfy certain assumptions,
Exactly.
Otherwise the Kalman filter doesn't work.
Exactly. And this is what you see here down. Both noises are white Gaussian. This means they are normally distributed, mean zero, and some covariance Q or R.
Right. And then there's a third distribution that is important for us in the context of the Kalman filter, which is the distribution of x0. What is this distribution
Exactly.
about?
So x0, this is basically our a priori knowledge about what we think the states are. Since we cannot measure directly, this is some hypothesis that we make about where the states are. This is centered around our a priori knowledge. We assume it is also a normally distributed variable with a certain covariance P.
Okay, perfect. So in this setting, we can apply the Kalman filter, and the Kalman filter is on paper a rather simple algorithm. It has commonly two steps. For example, they are called the correction and the prediction step. Sometimes you start with the correction step, sometimes with the prediction step. It really depends on your formulation of the Kalman filter. We start here with the correction step. Before we explain that, I'm just going to put it out here. So we are going to just show you this algorithm quickly, and then we are going to discuss why it works. But yeah, first let's show you this algorithm. Sergio, how does this work?
Yes, exactly. So you have seen the algorithm, maybe implemented yourself, and it's a very simple one. We compute what is called the Kalman gain L, and then once we have this Kalman gain, we are able to update our estimate, our a priori estimate that we have here xk hat with a minus. We use the Kalman gain to do this update. Yeah? To do this update, so to improve our, correct our estimate, we use this measurement information y here. We do the same with the confidence that we have on our estimate, and we can update this matrix P. And we do this recursively.
Right. And then also we do the second step, which is in our case the prediction step. And the prediction step looks like this. What is happening here?
Yes, because we are typically interested not only because we are considering dynamic systems, we are interested also on the estimate of the state at the next sampling time. So what we do is we propagate with the system dynamics our estimate. That would be like the center point of our estimate. Since we have a linear model, the propagation is very simple. We just apply our model, okay? And we can also, and because the distribution here it's everything Gaussian, we can propagate also the covariance of this estimate also in one step using system dynamics as we have here. So those are just the typical equations that you know from a Kalman filter.
Right. Yeah. So as we said before, this is the algorithm. You could implement it like this. But today we are going to focus on understanding where this algorithm comes from. We are not going to derive it because that involves some cumbersome linear algebra, but it's also not too difficult. But we're trying to understand where it comes from and also how to interpret the results that this Kalman filter is giving to us.
Exactly. So let's start.
Yeah. To do that, we have a look at a very simple example of where we can apply a Kalman filter, and that will help us a lot in understanding what is going on in a Kalman filter. Yeah, Sergio, could you explain to us the scenario that we are looking at here?
Yes. So we are looking at a very simple dynamic system. It is exactly the same setting as before, but we have only one state, x, and one output, y. Yeah, we can actually measure the state, so you can interpret this. We are filtering just the process and measurement noise. We have the same assumptions on the noise as before. Oh, Okay, so we are considering the same setting where the Kalman filter is valid. We have white Gaussian noise for process and measurement noise, and we have our initial estimate, our a priori estimate with a certain variance, sigma p.
Right. And this is exactly what we are now depicting here in the middle. So it's a normal distribution. Hopefully you have seen a normal distribution before. And we have this mean value for the normal distribution, and we have a variance for this normal distribution. How are these to be interpreted in the setting of Kalman filter again?
Yes, so again, what we are going to have here is a probabilistic description of the same concept that we have just described. So the probability of the state is going to be a normal distributed, which mean is our a priori estimate with a certain variance sigma p. This is what we have here, exactly as you just said. So that would be the center point here. That would be our a priori estimate, x hat 0 minus, and we have a certain variance. And what this means here is that whether we are very confident that what we think our estimate is exactly here, or we are not so sure, and it can vary a lot. And for example, if we make this variance sigma p smaller, this means we are more sure that the estimate or the states actually are here, and this distribution gets narrow and narrow, and narrower and narrower. And if we make the variance larger, what we see is that this distribution gets broader and broader. And this basically means that we are not so sure that our estimates are actually here.
Right. Yeah. So this is the first important distribution that we have to look at in the context of Kalman filtering and putting it back to like a medium uncertainty. The second important distribution we need to look at is the distribution of the measurements. In the context now in our, well, I call it Bayesian point of view, we are going to denote this with p y0 given x0. What does this distribution mean? How can this be interpreted?
Yes, this is interpreted because whenever you measure something, it's not completely independent from the actual state of of what you are measuring. Yeah, and that's why we always describe this as the probability of your measurement divided, given that, sorry, that's the symbol here, given that you are at some state x0. And this is the red distribution that you have here. Yeah, and we are assuming that when we measure, this is also normally distributed. Yeah, and it has a certain variance. Okay, and this is the red curve here. So you could imagine this value here is what you would get maybe from your measurement device, and the distribution is related to the accuracy of the measurement device. And just as before, if we could do now, for example, the measurement, the sigma r, the measurement noise much larger, this could mean that we have less accurate measurement. And you see that the distribution gets broader and broader, and you do not trust your measurement that much.
Right. Yeah. And the same is true if we make this very small variance, then the distribution gets slimmer and slimmer, or narrower and narrower. One side note that we need to make here is we can plot this in the same diagram because we are measuring the state that we are interested in, right? In the general case, this could be any measurement that is not related to this particular state, for example.
Exactly.
Yeah. Good. So now we have these two distributions. And what we are interested in is the posterior of our state, which takes into account information from these two distributions. How does this work in practice?
Exactly. And this is really what we want to do. Yeah, we have these two informations. How do we put this together?
Yeah.
Yeah. And you might think, just thinking logically or intuitively, like the real state, if you think that this is your prior, if you think the state is here and you measure something here, then probably reality is somewhere in between.
Right.
Okay. And this is actually the case. Yeah.
Yeah. Let me show that quickly for this particular example.
We can show you already here the result of what the actual Kalman filter would do. Yeah.
Yeah.
And you see that the intuition is correct. So the posterior is actually somewhere in between. That's going to be the mean of the posterior, and it has a certain variance. Okay. And the question is, how do we do this systematically?
Right. Yeah. And for this, we need to have a look at a specific equation, but we're going to do this in a second. Let's first experiment a bit with how this posterior behaves depending on our, well, measurement and our prior, because I think this gives a good intuition of what's going to happen. Basically, I would say we do the same as before. Let's just start by increasing, for example, the measurement noise and see how the posterior is going to develop. So that's what I'm doing now here. And yeah, what are we seeing, Sergio?
So if we now increase the variance of the measurement noise, yeah, we are trusting less and less our measurement because it is a bad measurement. And you see that the posterior shifts, and now the posterior is basically the same as our prior. So we trust our prior information, and our posterior is basically the same as the prior because our measurement is very bad. Yeah, this makes sense. If you have very bad measurement, then this is not telling you anything about the real states.
Right. Okay. And obviously the same holds for the opposite scenario where we have a trustworthy measurement, but now I'm increasing the variance of the initial state estimate. So yeah.
And again, if you are not so much confident about your initial state estimate, then your posterior is going to trust more and more your measurements because you have very accurate measurements.
Right. So all of this intuitively makes sense. Yeah, how is this computed in practice? For this, we need to describe this equation here at the corner.
Exactly. This is a very important equation in probability theory. That's Bayes' rule. Yeah, and it says that you can actually compute the posterior based on these two other distributions on the red and the blue one that we have just described before. So we have here the probability density function, so the distribution of the measurements and the prior, as that we had here just up. We have an additional term here in the denominator that you can consider just to be a scaling factor. It's not very relevant here. This is how you can compute the posterior, so the green curve, based on the other two distributions.
Right. And for Kalman filter, we are in the fortunate situation that this posterior is also Gaussian. We can see this here visually, but you can also prove that, of course. This is part of the proof that we are not giving to you today because it's not important for the intuition of understanding the Kalman filter. So you just have to believe us on that, basically. And yeah, essentially, if you were to perform these calculations that we're not showing today, what you would end up with is exactly the algorithm of the correction step of the Kalman filter.
Yes, so you can say that the correction step is just a way of computing this kind of Bayes rule, such that you can combine the knowledge about your prior and your measurement.
Right. So the correction step is therefore fully described. What remains is the prediction step. So let me show you the resulting prediction, and then we discuss how it comes out of these equations. So this is the resulting prediction of x1. Could you elaborate a bit, Sergio?
Yes, so we have here the posterior for x0, but we are interested, since we are dealing with dynamic systems, also in the state estimate at the next time. For that, we use our model, yeah? And we just propagate, as we had seen in the formulas for the Kalman filter before, we just propagate our model. And x0 is now a probability density function. It's basically, or it's a normally distributed variable. Is this green described by this green curve. So x1 will be also normally distributed because we are just multiplying and adding something what is also normally distributed. So the question is, we will have a normal distribution here with which mean and with which variance. Yeah. So the mean is simple because we have here just a multiplication of 2. So the mean of the propagated variable will be just twice the mean of the green variable here. Yeah, and you see here, this is something around 1.1, and you have here 2.2 mean.
Right, that is easy. And for the covariance or for the standard deviation, the computation is in fact also fairly simple. It's easier to express it in terms of the standard deviation in this case. So because the standard deviation, we can also just multiply by this factor. So in this case, the standard deviation is now twice as large. But what we also need to take into consideration is that additional uncertain variable, which is the process noise. Exactly. So we need to incorporate that as well.
Yes, you need to incorporate also so the uncertainty of the standard deviation of the states at time 1 will be twice the standard deviation of state at time 0 because of this multiplication, and then you add up an additional random variable, and then the uncertainty, the standard deviation, will add up to, and therefore you will have a larger standard deviation. We can see this, for example, here. If we increase now the process noise, you will see that this distribution will also broaden, and this is because the standard deviation of the time of the state at time 1 will be broader because we have larger process noise.
Right. And we can also see that in the original equations for the Kalman filter. So for the prediction step, we have here this propagation of P.
Yes.
And yeah.
And you can see also this adding of the process noise exactly to the covariances we have just described right now.
Right. Yeah. I think this is the most important aspect about a single step of the Kalman filter for this very simple example. Just a final side note to that is, of course, the process now repeats. So if we do this Kalman filter recursively, our x1 at this time step becomes the x0 at the previous time step.
Exactly. And we can continue and do this for a whole trajectory of states that we have of a dynamic system. And this is exactly what we are going to see in the next part, where we apply this to an more interesting dynamic system.
Right. So let's get to this part. And yeah, my first question to you, Sergio, would be, could you quickly explain what kind of system we are looking at, what kind of setting we are looking at here?
Yes. So this is a simple dynamic system. It's a continuously steered tank reactor where we describe the evolution of the concentration of three components, A, B, and C over time. We have constant volume because it's a CSTR. We feed in some component of Ca, and there are some chemical reactions taking place, okay? This is continuous time. Since we are talking about the Kalman filter in discrete time, we can discretize this system and formulate it in this exactly same setting as before, where we have A, B, C matrices, process noise, measurement noise.
Right, so nothing has changed. The only difference is, in comparison to the previous step, is that everything is now a vector. So P, Q, and R are matrices instead of just a single scalar value. But apart from that, and of course the algorithm that we have shown on the first slide is also working for matrices as well. Yeah, very good. Then here in the center, we see a depiction of a scenario of how this process might look like. And yeah, could you elaborate a bit what that shows in particular?
Yes, so we have here just the distribution, or basically the trajectories of the system states CA, CB, CC. Okay, that's time, and that's how the evolution of the concentrations according to the discretized version of these differential equations would look like.
Right. These we don't know, so we only measure something, and that something is in this case the
CB, yeah, this state that it's this is what we are going to measure, and based on these measurements, our goal with state estimation is to be able to reconstruct the states at any point in time.
Right. Okay. I've added the state measurements, or the measurement of this single state CB now to the plot. Let me show you that a bit more in detail.
Yes, and you will see here that the measurements are depicted with these dots. Yeah, you are measuring at these points, and you see that they are not exactly on the line. This means there is some measurement noise. Yeah? And here the measurement noise is still rather small, but we can also say what happens if we increase the measurement noise, and you see that the points deviate more and more from the dashed line, what is the reality, increasing the measurement noise.
Right. Yeah, so that's the setting we are in. 3 states exist, we only measure 1. Now we want to estimate the rest of them, so we use the Kalman filter. The algorithm we have seen, so let me now add the estimated states to these figures. And yeah, Sergio, could you explain to us what we're seeing now?
Yes, so in each one of the figures, we see now a continuous line, and these are the state estimates that we obtain by applying just the Kalman filter algorithm. And you see that we start with some initial estimation error because we don't know the initial estimate. We have just some guess about it, and an estimator is working properly if after some point then we actually are able to converge to the real trajectory of the states. And this, you see, this is what's happening. We can, again, only measure this, but we are able to reconstruct the 3 states.
Right, so we can see here that the estimator is working as expected, but we are not using all the information that the estimator gives us, because as we have discussed on the previous tab, we also get some sort of uncertainty quantification from a Kalman filter, which is not shown in this figure just yet.
Exactly. And understanding this probability interpretation that we have just seen can help us also a lot in knowing whether our estimation is working properly, or knowing even more information than just what we are showing here. And this is exactly what we can have a look at.
Right. I will show the plot of how it looks to depict this uncertainty information, and then we explain a bit where this comes from, okay? So now I'm adding this uncertainty bounds here as this shaded area. But yeah, the question is where this comes from, and I think to explain this, I will quickly choose to, or will quickly switch back to the previous tab.
Exactly.
Yeah.
Yes, and you saw that shaded area here. That's gonna tell us a little bit about how certain we are about our estimates, but where is this coming from? to understand that shaded area, you have to look at this diagram. Yeah, this is the confidence about your estimate. Yeah, you have your posterior estimate. So once you have done the correction, the prediction step here, but this has a certain standard deviation here. Okay, so how can we represent that in a temporal plot? What we typically do is that we take just the 3 sigma intervals, so 3 sigma to the right, 3 sigma to the left, and you probably know when you have normal distributed variables, then if you take 3 sigma on both sides, the amount of probability that is inside of that region is actually 99.7. So this is describing almost all possible values of that variable. And we have this region here, or 3 sigma center around your estimate. And this is exactly what we can see in the next tab, is that shaded region that we were seeing on the top.
Right. Just 2 more comments about this. The first one being that in this scenario, we had a scalar distribution. So we only had a single variable that was uncertain. In our CSTR example, we have actually a vector. So our matrix P, our uncertainty, is also a matrix. So the question just quickly, how do we get from that to having a single 3 sigma for a sigma for each of the 3 states?
Exactly. What we do is we do have access to the P matrix in our Kalman filter algorithm. We see that we always perform also an update, not only on our estimates, but also on the covariance matrix on our P matrix. Yeah. And what we do is we can take a look at the elements on the diagonal of this matrix, sigma P squared, that's the variance of the state 1, sigma P square of state 2, sigma P square of state 3. And these elements of the diagonal, these are going to give us the variance of each one of the state estimates. And if we take the square root, then we have the standard deviation. We have the sigma. Okay, and the covariance is, in reality, it has also some values here that describe the covariance between different states, but they are not going to be relevant for the visualization. We typically focus on the variance of each one of the states, which are just the elements on the diagonal of that P matrix that the Kalman algorithm is giving you.
Yeah, perfect. Then now let's have a look at what this uncertainty band actually shows us. I think in particular, the first concentration of CA is quite helpful for that. I'm zooming in here a bit. So yeah, what are we seeing here? How is this uncertainty or this 3 sigma environment helping us?
What you see is that you have some estimate, that's the continuous line here, and you plot the 3 sigma, and what this is telling you is that the real state of the system will, with a very high probability, 99.7%, actually lie within that interval. And you see that this is actually real, yeah? The real evolution of the system is between those intervals, okay? And this is really, really helpful because it's not only, you don't only have an estimate, but you know also where actually your real state might be.
Right, yeah, that's of course a very useful information. And just to emphasize this again, because the Kalman filter is the optimal filter in this scenario, we can actually guarantee that this property is satisfied and that we are neither over nor under confident. So this 3 sigma environment is also not too broad, which is of course also important, because if we just assume we have a super broad distribution, then this information is not very helpful either.
Exactly.
Yeah. There is one problem, however, you see this a bit here, because here in the very beginning, we see that we are actually not having the true state within the 3 sigma environment of the estimated state. Can you explain to us where this comes from?
Yes, this comes from, as we said before, yeah, we need to start the estimation from somewhere. So we have some a priori initial estimate, and that's exactly what we have here in the initial estimate. So this is where we think our states start, because we cannot measure them. This is where the real one starts, yeah? So there is a big distance there. But we also need to tell our algorithm what is the confidence about that initial choice that we have made, yeah? What is the confidence that the initial state is there? And this is what we typically do, another tuning algorithm of the Kalman filter. That's what we call typically the P0, yeah? So what is the covariance at time 0, yeah?
Right.
And depending on, in that case, we are telling our algorithm we have a very small covariance there. We are very confident that this is the initial state. And of course, if this is not true, then we may encounter this problem.
Right. So what we can do to fix this is we can increase the covariance of this initial state what we do in practice is we have just the same variance for all of the 3 states, and we multiply this by a diagonal matrix. So we have a very simple parameterization of this P0, but often that is useful in practice.
Exactly. So you will see here that we change only one value, and that's basically just what we are changing is just the values of the diagonals, because we assume that P times 0 has here the same values and has the diagonal matrix like this.
Right.
Okay.
And that's what I'm doing now. So I'm increasing this initial state covariance. And what you are seeing because of that increased covariance, at some point, we do in fact include this true initial state in the 3 sigma environment of the estimated state. I'm zooming in here a bit so that we can see it a bit better.
Exactly. And you see the initial estimate is still in the same position as before, but we are telling the algorithm, okay, we are not so sure about the initial point, and now the uncertainty information is including again the actual distribution. Yeah, you can see here also that the assumptions that you make in the Kalman filter might sometimes give some problems with physical quantities. Yeah, because here you see that this is telling you the concentration might be negative at some point, but you know that this cannot be true because there are no negative concentrations. So you just need to keep in mind that you have these assumptions about normal distributions. They do not have to hold all the time.
Right, yeah. And one other thing to notice here because of that change of this initial covariance is that, especially in the beginning, we are trusting our measurements more because we are very uncertain about the initial state. So not only did we now change the uncertainty range in this very beginning, we also changed how fast we can converge to the true state because we are not really trusting our initial estimate of the state. So those 2 effects are both very important. It's not only about the uncertainty here. Yeah. So after having discussed all of that, I would say we do a couple of experiments to show a bit how the Kalman filter performs depending on different scenarios. And most importantly, after having discussed now this initial state covariance, we can change 2 things, and that is the measurement noise and the process noise. Yeah, so I would say we start by having a look at the effect of the process noise. So let me just increase that and you explain to us what is happening because of that.
Yes, so we are increasing now the process noise here, and you see here that the size of this 3 sigma band here is increasing. Yeah, but this doesn't mean that our filter or our estimator is not working fine. It is actually describing reality, because if you have a higher process noise, this is real. Yeah, this means that your process is actually changing. So even if your estimator is working as best as possible, you cannot make your confidence here smaller. But because, as you see, yeah, the real system is actually varying a lot. So you can only do some estimation with a certain confidence. If you have a lot of process noise, this confidence band will be larger. But still, your region here is properly encapsulating the real evolution. It's not very broad. It's not underestimating it.
Right. So in some other way, we could also say that the effect of the unmodeled behavior of the system become more and more important. And we encompass that in this higher uncertainty band of the estimated.
Exactly. And this is something that you would miss if you only look at the estimate. Yeah?
Right.
If you don't take into account this probabilistic interpretation.
Right. If we, on the other hand side, decrease the process noise by quite a bit, then we have a very different behavior. So, Sergio, could you explain a bit?
Yes, it's very simple. You see here, the band here is very, very small. Even though if we zoom, we can still see a small band. But what this means basically is that, well, we are now very, very sure that after some point, after some time, we are really confident that our estimate is very, very close to the real state.
Right. Yeah. But as you said, if we zoom in far enough, the behavior looks very similar to what we have seen before. We have this jiggly behavior of the true states and the band of the uncertainty encompassing this behavior entirely. Yeah, so much for the process noise. Then I would say I'm putting this back on a medium level. And we now have a look at the effect of the measurement noise.
Exactly. So if we increase now the measurement noise, you will see that the noise here increases. And the effect that we see in the estimator is that because we are not gaining so much information from our measurements, then it takes longer for our estimates to convert to the real state trajectories.
Right, that makes sense. And on the opposite, we have a very low measurement noise, which I'm setting up now. And yeah, what's happening because of that?
Because of that, then, of course, as you may imagine, now we can really very, very fast, because we are gaining a lot of information very fast from very accurate measurements, we can very fast convert to the trajectory of the real states.
Right. Yeah, I think that is the most important behaviors that we wanted to discuss. There's just a couple of important side notes. The first one being that, of course, in practice, what we are setting if we are tuning a Kalman filter is just our expectation of the process and of the measurement noise. And we are not, in fact, changing the process and the measurement noise of the real system. That is something that we do not really influence, right?
Exactly. Yeah, we just choose some values for those Q and R matrices that we think are close to those in reality, but of course we don't directly influence the accuracy of our measurement device, or we don't directly influence the process noise that is actually there in our system.
Yeah, but if we choose correct values and if, the other assumptions also hold, then we have a very valuable additional information, which is this uncertainty range of the estimated states.
Exactly.
Yeah. Good. So I would say that concludes our explanation of the Kalman filter. We hope you have learned a lot about the Kalman filter, how to interpret it, how to tune it, and also how to gain additional insights by, for example, using this uncertainty range, which is very important also in practice.
Very good. Thank you very much. You will have also this tool available. Just follow the link in the description. And thank you very much. See you in the next LightPod.
Thank you. Bye-bye.